In this lecture, we will consider an important property called the heat capacity of a system. Heat capacity is defined as the amount of heat required to raise the temperature of a system by 1 degree. And we'll denote the heat capacity by capital C. And heat capacity per unit mass of the substance is defined as the specific heat capacity, or simply the specific heat. And we'll denote the specific heat by a lowercase c. In the previous lecture, we've seen one example where we had this piston cylinder arrangement with a gas, and we saw that heat is added to this system while the pressure was constant throughout this process. Similarly, we could have also added heat while keeping the volume constant, let's say by adding some stops over here so that the piston did not move. So heat can be added in various processes. Two specific processes which are of interest are constant volume and constant pressure. And there could be other processes and many other processes where heat could be added. Clearly, the heat that is added during a process will depend upon the type of the process, and therefore the heat that we'll have to add to this gas, let's say, while keeping volume constant or while keeping pressure constant to raise the temperature of the system by 1 degree is going to be different. Therefore, when we talk of heat capacity, we need to define the process in which we add this heat to the system. Therefore, we look at two types of heat capacities. One is the heat capacity at constant volume, which we'll denote by C subscript V, and the specific heat capacity at constant volume we'll denote by lowercase c subscript V. Whereas at constant pressure, the heat capacity corresponding to heat required to raise the temperature by 1 degree while keeping pressure constant is denoted by Cp, and the specific heat is denoted by the lowercase c. So mathematically, heat capacity can be defined as, so C is equal to the heat that we add to the system divided by the change in temperature, and we look at the limit when delta T tends to 0. This is the mathematical definition of heat capacity, and this is equal to dq by dt. But we must also specify what is held constant, volume or pressure or any other thing. So in this case, we'll have to define what is kept constant. So if the volume is kept constant during this heat addition process, then we'll define the heat capacity at constant volume as dq by dt. But let's specify what is kept constant during this process. So we'll use a subscript V over here. Similarly, to define the heat capacity at constant pressure, we have dq by dt, and what is kept constant? It's pressure, so we'll write pressure in the subscript over here. So in thermodynamics, you will see that it's convenient to clearly and explicitly mention what are the variables that are kept constant during the process. So you'll encounter derivatives in brackets, and we'll always write the variables that are constant during that process. Now let's consider a homogeneous system of a pure substance, and that substance could be a gas, could be liquid or solid, but by homogeneous we mean it should be in the single phase. Therefore, if we have a homogeneous system of a pure substance on which we do mechanical work, then we can get this relation for the heat capacities by using the first law. So this is what we do. So we start with the first law for a control mass, that is du equals to dq minus pdv. Now what we want is to express this du in terms of some partial derivatives with respect to other thermodynamic properties. So what properties should we choose? We've seen in the previous lecture that we could choose u as function of t and v. We could also use u as function of t and p. That means we could choose any two independent variables to describe the state of the system. But because we are interested in calculating heat capacity at constant volume, it makes sense to use T and V, that is temperature and volume, to define the state of the system. So if we do so, we know that U is a function of T and V. Therefore, du I can write as del U by del T times dt plus del U by del V times dV. And we'll also state what is the variable that is kept constant while taking this partial derivative, and in our case this is volume over here and temperature over here. Now we can substitute this relation over here. So when we do so, we'll get dq is equal to, first we'll have this pdv which we take to the other side, then we have this relation for du, and let's write del u by del t at constant v times dt plus del u by del v at constant t times dv. Now for a constant volume process, we have dv equals to 0. That means in this equation, this term is 0 and this term is 0. Therefore, the only two terms are dq and this particular term. Therefore, dq by dt, and we've noted that volume does not change, so at constant volume is equal to del u by del t at constant v, and this is my heat capacity at constant volume. And if we were to look at the specific heat capacities, then we would write Cv is equal to the derivative of the specific internal energy while keeping the specific volume constant. So what we see over here is that the heat capacity at constant volume is related to the different thermodynamic properties, that is the internal energy, temperature and volume. Therefore, the heat capacities are also thermodynamic properties. Because this derivative of internal energy with respect to temperature while keeping volume constant will depend only on the state of the system. It's not going to depend upon the path that is taken by the system. So heat capacities are also thermodynamic properties, and the heat capacity is an extensive quantity and the specific heat capacity is an intensive quantity. Next, let us look at the case when volume is not constant, but instead pressure is kept constant during heat addition. That means what we want to get is the relation for heat capacity at constant pressure in terms of other thermodynamic properties. So this time, because we want to keep pressure constant, it is convenient to choose T and P as the independent state variables or variables to define the state of the system. Therefore, we have internal energy is a function of temperature and pressure. So internal energy of a given mass of substance is a function of temperature and pressure. And now we can write du as del u by del t while keeping pressure constant times dt plus del u by del p while keeping temperature constant times dp. And from the first law, this is equal to dq plus dw, and dw is, in this particular case, minus pdv, because we are just looking at the mechanical work. Now we have t, dt, dp and dv, but the independent variables to define the state, we have taken them as t and p. So let's expand dv. So we can write dv also in a similar fashion. So let's write dv as del v by del t at constant p dp plus del v by del p at constant t dp. So this is dt. And we can do so because there are only few independent state properties and we can choose them arbitrarily. So T and P are the properties that we are choosing to be independent, and all other properties, volume, internal energy, etc., would depend upon these two properties only that we have chosen. Therefore, now we have dq minus p, and we'll substitute this relation for dv over here. So we get del v by del t at constant p dt plus del v by del p at constant t dp. Now for constant pressure, process, which is also called an isobaric process, we can simplify this equation. And just like we call a constant pressure process as isobaric process, we call a constant volume process as an isobaric process, because when volume is constant, there's no work involved. So for an isobaric process, we have dp equals to 0 because p is constant. Now looking at this equation for the first law, so if dp is 0, we can get rid of these terms. Therefore, dq is given by this equation, because the dp terms will be 0. In other words, dq by dt at constant pressure, because this equation is for constant pressure, so dq by dt at constant pressure is given by del u by del t at constant pressure plus pressure times del v by del t at constant pressure. Because pressure is kept constant, we can also write this as del by del t of u plus pv, and we keep pressure constant. Now if you recall, this term u plus pv we have defined as enthalpy. Therefore, my heat capacity at constant pressure, which is defined by dq by dt at constant p, is equal to del h by del t at constant p. And this relation for heat capacity at constant pressure in terms of enthalpy H is not surprising, because we've already seen in the previous lecture that heat addition at constant pressure is equal to the change in enthalpy. Again, this expression for heat capacity in terms of enthalpy, temperature, and pressure tells us that heat capacity at constant pressure, because it depends upon H, T, and P, is also a property, because it does not depend upon the path. So if we have, let's say, a particular state given by pressure and volume, or let's say by, in this case, pressure and temperature, so no matter how we have arrived at this state, this derivative del H by del T at constant P is going to be the same. Therefore, heat capacities are themselves thermodynamic properties. And note that here we are looking at the heat capacities. We could have done a similar derivation in terms of specific heat capacities. So the specific heat capacity at constant pressure would be given as the derivative of the specific enthalpy with temperature while keeping pressure constant. Now that we have seen definition of two heat capacities for two processes, constant volume and constant pressure, let's see what is the difference between these two heat capacities. So if you look at this particular system over here, where you are adding heat and the gas expands and goes from temperature T1 to T2, then the amount of heat that we need to transfer to the gas will depend upon whether the pressure was kept constant or volume was kept constant. Clearly, because if volume is kept constant, then there will be no work involved. Whereas if we keep pressure constant, there would be some work involved, and therefore the heat that is transferred to the system to take it from one temperature to another temperature is going to be dependent upon whether you kept volume constant or pressure constant. Therefore, these heat capacities Cp and Cv are in general different, and they are not the same. So let's look at how we can find the difference between these heat capacities. So what we'll do is, let's start with the internal energy, and we'll choose T and V as the independent properties. Then I can write a du as del u by del t at constant v times dt times del u by del v at constant t times dv. And we can write this because u is some function of t comma v, and because we are choosing only two properties which can be changed independently, that's why when we take partial derivatives we explicitly mention which of the property is kept constant. Now we clearly know that this quantity over here is my heat capacity at constant volume. So I want to derive a relation between heat capacity at constant volume and heat capacity at constant pressure. Therefore, what we'll have to do is to introduce pressure. So now what we'll do is we'll define the state of the system using T and P, that is temperature and pressure, as the independent variables. So anytime I can choose any two variables because we are considering a homogeneous system of a pure substance. Then if U is a function of T and P, we can write du as del u by del t at constant P times dt del u by del p at constant temperature times dp. Let's substitute this over here. If we do so, what we'll get is this will be equal to this term over here. And now we want to keep P constant. So if we keep P constant, then V is not going to be constant. So how V is going to change is that we can write this dV as, so instead of this dV, we'll say that there's a term which is del V by del T at constant P dt, because I can write V as function of T and P, and therefore dV in terms of the derivatives with respect to temperature and pressure. So instead of dV, we can write this, where this is the multiplication with this del u by del v at constant T term. Now we can simplify this equation for a constant pressure process for which dP equals to 0. So if I set dP is 0 over here and dP is 0, what we are left with is this term, this particular term, which is simply Cv times dt, and one additional term over here, that is the product of this quantity and this quantity. To simplify, let's write this as del u by del t at constant P dt is equal to Cv dt plus del u by del v at constant t times del v by del t at constant P dt. So we can cancel off dt on all sides. Now we can introduce, let's say, instead of u, because we have P constant, instead of u we can write this term better in terms of h. So we'll say u is h minus pv. Therefore this term over here would become del h by del t at constant p minus, so we have derivative of del P V by del T, but because pressure is constant, we can take it out of this derivative and we have minus P dV by dt at constant P, and that is equal to Cv from here plus this particular term. Now recall that this quantity over here is the heat capacity at constant pressure. So we can write Cp minus Cv, that is this term, is equal to P, this term, plus del U by del V at constant T times, so this term del V by del T at constant P is common and that comes here. So we have derived a relationship between the difference between the heat capacities at constant pressure and volume in terms of other thermodynamic properties, that is pressure, internal energy, volume and temperature. And this difference in Cp and Cv comes from the work done at constant pressure, because there's no work involved at constant volume. And we can also write this equation in terms of the heat capacities per unit mass, that is the specific heat capacity. So Cp lowercase c P minus Cv will be equal to pressure plus the derivative of the specific internal energy with respect to specific volume while keeping temperature constant times the derivative of specific volume with respect to temperature while keeping pressure constant. Now note that this term over here can be written in terms of another property, and that property is called the coefficient of thermal expansion. So coefficient of thermal expansion we'll denote by beta is given by this, that is at constant pressure the volumetric change due to the change in temperature, and that is the relative change, so that is 1 over v factor is over here. So this is called the coefficient of thermal expansion. Therefore we can also write Cp minus Cv in terms of beta as P plus del U by del V, and this is the specific internal energy times V times beta, and V is the specific volume. So in general, Cp is greater than Cv. However, for solids and liquids, this coefficient of thermal expansion is rather small. Therefore, this term on the right hand side is very small. Therefore, for solids and liquids, typically the heat capacities at constant pressure and constant volume are approximately the same. But this is not the case for gases, and in the next lecture, using an example of an ideal gas, we are going to see what is this difference in the heat capacities at constant pressure and constant volume. So what we have done in this lecture is that we used the first law of thermodynamics to derive relationship between the heat capacities. So first we started off with the definition of heat capacities, and then we were able to express heat capacities in terms of other thermodynamic properties. And then we were able to derive a relationship between these heat capacities and other quantities. For example, we found that the difference in heat capacities depends upon the coefficient of thermal expansion. So that relation might not be obvious, but thermodynamics allows us to do so. Now recall that when we looked at Introduction to Thermodynamics, we said that thermodynamics deals with energy conversion processes and the relationship between properties that are involved in these energy conversion processes. And this relationship between heat capacities at constant pressure and constant volume is an example of how we can use thermodynamics to get relationship between different properties. And during our introduction to thermodynamics, we also said that we cannot get the values of these heat capacities from thermodynamics. So thermodynamics will not tell us what is the value of Cp and Cv, but we can get a relationship between these properties. So this is an example where we are able to express the difference in the heat capacities at constant pressure and constant volume in terms of other quantities. In the next lecture, we'll look at the application of the first law of thermodynamics to ideal gases, and there we'll also see how this relation between Cp and Cv simplifies.